So 6.4 is arc length. I don't know if you guys remember this, but back in the day when we first started this class, we actually did some of this estimation work on arc length. You guys remember that? It was like the first, literally like first day of class. And it looked something like, this, whatever. Got f of x going from here to here. And we were like, hey, how would you estimate that arc length? And you were like, oh, easy, distance formula, right? In fact, you could just find the distance formula between the two endpoints, and that would be somewhat of a ballpark estimate, right? But not super great. And then what'd you do to get a better estimate? Infinite intervals of division of this thing, adding them all together, right? So basically, this is far from infinite, not to scale, but basically you broke it up into subdivisions and used the distance formula. And it was like a finite number, like 4 or 5, something like that. It wasn't too horrible, but now it's going to be horrible. Actually, it'll be easy with integration, but that's what we're going to be going towards, right? Moving towards an infinite number of subdivisions. So let's just talk about where this formula comes from so that you can kind of see it. And if you recall, distance formula could be written like this with summation notation. Now, you're not going to have to use summation notation, obviously, right? Since we're second semester calculus. But it had something like this, I equals 1 to n, driving n to hugeness, right? Isn't that nothing more than the square root of x1 minus x2, the quantity squared? Now, by the way, when you take x1 minus x2, do you guys agree you essentially get the change in x? I mean, that's what you're finding, right? It's the change in x between the two x values, right? So I could write it like this. This is like delta x sub I, and then I'll square that. It's supposed to be a delta. And I is the ith subdivision, basically, right? As I work my way across from 1 to like 8 trillion subdivisions. That'll just be like the little bitty change in x, basically, right? And I'm going to add that to, likewise, I'll use the same notation here. This will be delta y sub I, and I'll square that. So this is like a weird way of writing x1 minus x2, y1 minus y2, as I work my way across from like whatever that is, 1 to 7 along the x-axis, right? Perfect. So what I'm going to do now is I'm going to take this and I'm going to pull out a delta x squared out of these two things. Everybody follow me. All right, so let me write it out. This is going to be the sum of the square root. This gives me delta x sub I, the quantity squared. What that's going to leave me then is 1 plus delta y sub I over delta x sub I, the quantity squared. Kind of skipped a step there. Does everyone see what's going on? As opposed to writing this as delta y sub I squared over delta x sub I squared, I just combine them into 1, right? How we doing, people? We okay? Sweet. Now what I'm going to do is I'm going to square root the delta x sub I. So what this give me? The sum from I equals 1 to n, the square root of 1 plus delta y sub I over delta x sub I, the quantity squared, and this will give me delta x sub I on the outside. Won't it? Hey, listen, the square root of a product is equal to the product of the square roots, ain't it? Say it one more time. The square root of a product is equal to the product of the square roots, right? So I could do this as the square root of this times the square root of that. Just take care of that. That comes outside. That's what you did back in the day with the simplified radicals. Sorry, Cal. Okay, so you can already see what's going on here. This is the old school notation. The new school notation for arc length, I'm going to use S for that, will be the integral, right, from, say, A to B, wherever the arc starts or wherever this arc ends. And then this will be the square root of 1 plus, what do you think delta y over delta x is? Slope. Oh, isn't it? Listen, especially if n's going to hugeness. Olivia's right. This is an infinitely tiny little increment of movement along the y over the x, right? So isn't this going to be f prime of x, the quantity squared, and then my teeny little increment of movement along the x will, of course, be written as dx, which is consistent with how we wrote all the other units of measure. Fascinating. That's basically it. It's at least part of what we're going to be doing in 6-4, right? All right, so work through a quick problem here. Let's say that I had something like, oh, hey, by the way, and incidentally, the nice thing about this section, as opposed to like disk, shell, and washer, you can work these problems in any variable that I give you. Actually, that one more time. You can work it in any variable that I give you, right? Because these little increments of movement along that arc are basically individual points. They're so small. So you don't need to rewrite anything in terms of X or anything in terms of Y. Just let it roll. Everybody with me? Okay, cool. So if I had something like this, let's say that f of x is equal to x to the, actually, let me, this is a little easier. 3/2 x to the 2/3 over the interval from 1 to 8. And I'm looking for arc length. Let's go ahead and set this up. Evan, how do I write this integral?
It's the integral from 1 to 8.
Love it.
1 plus that is
I think that is right? So that comes down to the front. That gives you 1. This is going to be x to the negative 1/3. That thing squared. Dx. You hanging in, Zach?
Does the 3/2? What happens to the 3/2?
3/2 cancels with the 2/3. Right? It's been a while since we derived, right? So isn't it 2/3 times 3/2? Take 1 away from the power. Well said, Kyle. Beautiful, beautiful, beautiful. Let's go ahead and clean this up a little bit because these, again, I want you to actually work through, right? So isn't this from 1 to 8? This will be the square root of. This is 1 plus 1 over x to the 2/3 power dx. Everybody hanging in? This does not look u substitutable yet. Does it? I don't think so. All right, so let's go ahead and get common denominator. Yep, you got it, Evan. So isn't this then going to go to the integral from 1 to 8? This is the square root of. It's going to be x to the 2/3 plus 1 over x to the 2/3 dx. We're getting there. But now you're hanging in, right? Love it. Also, you got the root of a product is equal to the product of the roots. The root of a quotient is equal to the quotient of the roots. Ain't it? Beautiful. Isn't this the same then? It's 1 to 8 of the square root of x to the 2/3 plus 1 all over x to the 1/3 dx. Pilar, you hanging in? Love it. How are we doing, people? I think we just about got it, don't we? I can actually take this up to the top if I wanted to. This is from 1 to 8, square root x to the 2/3 plus 1, x to the negative 1/3 dx. True? Just brought it up to the top. Hey, the problem is this, though. I still do have a quantity other than x raised to a power, and I do have a product. Skylar, have I lost you anywhere, or are you okay?
Can you explain one more time how you got from the square root over
Here
the
to
whole
here?
thing? Yeah.
Yeah, you got it. You got it. So I just broke this up into 2 different square roots. Do you agree that if I take x to the 2/3 to the 1/2, I get x to the 1/3 in the bottom? Power to a power, you multiply the powers. I just didn't write that out. Does that help? Love it. Love it. Hey, Noah, what is you?
X to the 2/3 plus 1.
Beautiful. Gavin, drive it for me.
X to the negative, or sorry, it's 3/3 x to the negative. Yeah.
Ain't it? Well said. Bring that over to the other side. Don't have 2/3. Hey, Cal, what's that substitution?
3/2 and 1 to 8 of root u times u.
I believe that's true. By the way, don't forget back in the day, this is actually wrong, isn't it? Shouldn't these be U bounds? Or remember how we did it? I want to get everything back in terms of x, and I keep 1 to 8, right? All right, cool. Sarah, and I drive this for me, please.
That would be 2 and 2 u Yeah, 2U. Yeah.
So this would be 2/3 times that. I think it's just U, isn't it?
Yeah.
Hang on, is that right? I think that's right.
Yeah.
It's gonna be 3/2, U to the 3/2 over 3/2, or 2/3 times 3/2, which is 1 here, right? So isn't this gonna be then, what is that? X to the 2/3 plus 1, all that to the 3/2 going from 1 to 8. Now I can keep 1 to 8, correct, Ben? Beautiful. Make sure I'm still on camera here. Whoops. All right. Take 8, take 1, plug them in that order, subtract it, correct? By the way, if I take 8 and plug it in here, is this cube root squared? 4 plus 1, that's 5, to the 3/2. By the way, this is going to be irrational, right? If you use your calculator on this. How we do it, people? Good. Now, by the way, I would probably just leave it as like 5 to the 3/2 minus whatever that is, 2 to the 3/2. Just leave it just like that. Because you're probably going to be doing this on a non-calculator portion of your test anyway. Go ahead, Sarah.
So I'm just a little confused. So how do you get summation?
Yeah,
How can you just like slap an integrand?
but because it's the same thing.
Because like because we've always used it to find area.
That's exactly right. But if you remember the immediate precursor to the integrand, the first fundamental theorem of calculus, let's say, take you back here just for a second. If you guys remember this, we would do this. Wouldn't this be 2 over n? F of 1 plus 2 over ni. You guys remember this? Maybe. No, not really. Okay, great. So then what I did was I took this, I plugged it in there. This gave me the sum of 1 plus 2 over ni squared plus 1. All that times 2 over n. I just flipped them. But you guys with me? And then we tired of this. You quickly tired of this. Yes? And so we said, well, you know what? Hey, we can just outright this like this. Because isn't it true, tiny movement along the x-axis? That's dx. Didn't I get this by just plugging it into f of x? So this is height, width. It's exactly the same thing. Exactly the same thing.
Okay.
And that's how I can make the leap from summation to integration. It is the same thing, just different notation. It's actually kind of cool. We good on this? All right, one more thing to show you. Almost finished. You guys hanging in 10 minutes? These block days are killer. Because we're not only doing arc length. Actually, I got 2 more things to show you. Sorry. So just to set the table, I need about 15 minutes. Okay, we got it? Then you'll have an hour to work and relax, get up, walk around, do push-ups, whatever. Okay, sweet. All right. We're going to do arc length. We're also going to do surface area. When I take that arc length, revolve it around axis of revolution. I know it sounds painful, doesn't it? We got this, though. All right. So let's just go back to my example. Say I take my arc length and I revolve it around the x-axis. Now what you'll notice here is, guys, that you do not have a bounded two-dimensional area, right? I'm just taking this piece of rope and I'm just revolving it around the x-axis. So do you guys agree you're going to get something that looks...
You get the cone shape.
You do. That's exactly right. Exactly what dogs wear. I had surgery. It's supposed to go down a little bit more, but right? Or like a lampshade. But it's just area. There's no volume, right? So taking a single line and just revolving it around that. So I want to see what we're doing here. Sweet, cool. So what I want to do then is this. In order to calculate this area, what I'm going to do is I'm going to take a little bitty piece of arc length. okay? And I'm gonna revolve this piece of arc length around that axis of revolution. And would you guys agree that I get like a paper ring? If I just look at that just that one. You guys know what I'm talking about? Just a ring of paper, right? So then if I take some scissors and I cut that paper ring right there and I just lay it out, I'm gonna get that, aren't I? Infinitely thin. You guys all with me here? Well, would you agree that this dimension right here is arc length? Isn't it? That's what I'm calculating, right? I'm adding up all that arc length. What's this? I think I heard it. Somebody said it. It's circumference. Isn't this 2 pi times radius? So you take arc length times 2 pi r, you got it. Wait, Gavin, what'd you say?
What?
Nothing. Okay, I thought you said something. Who was it? It was Kyle doing a Gavin impression. That was amazing, by the way. Go ahead.
Wouldn't R be Y?
Oh, that's a great question. R in this case is y. What if I was going around the y-axis? What would it be? It'd be x. That's a beautiful. You guys are doing great. Perfect. So check this out. Let's say, let's see, do I have work to do? Oh yeah. It's exactly like disc, washer, shell. Axis of revolution up to the curve. In this case, that's nothing but y, right? Beautiful. So what if I had something like this? Y is equal to 4 minus x squared. And I want to go from 0 to 2 along the x-axis. And this is going to be about the y-axis. The y-axis, right? And by the way, yeah, this picture, it'd be something like this, right? Something like that, from 0 to 2. Be that arc length right there, going around the y-axis. Here we go. Integrate from where to where, guys? That's going to be given in the problem, right? It'll be super easy to see. That is an x-axis interval. Everything's given in terms of x. I'm going to work it in terms of x, right? 0 to 2, I got 2 pi out front. Partial credit. Sweet. Arc length is nothing more than this, the square root of 1 plus what, guys? Got to be the slope. Times dx. Sarah, right?
Where are you getting that?
Where am I getting negative 2x, Jonathan?
You derive
It's the derivative of f, not f. Derivative of f, right? Derive it and square it, right? Perfect. Now, wait a second. I got to have r out here. What's r? I think it's just x if I'm going from here to here, right? Isn't that just x? How we doing, people? We okay?
Why is this? Yeah.
This is a dx problem because here again, you can work it in whatever variable you want. This paper ring that I have right here, you could even think of it as a line. It's so thin. This is like individual dots being taken around an axis of revolution. There is really no like dimension that requires you do it in terms of x or y. You can do it freely in terms of x or y. If I give it to you in terms of x, keep it in terms of x.
Okay.
I hope that makes sense, doesn't
Yeah.
it? I mean, it's just like a piece of thread, basically, and you're just adding out the area of all those threads. Yes, Sarah,
What's the
this is the radius.
oh,
2 pi r times arc length.
Because I was like, oh, it shouldn't be a dy problem. It'd be like 0 to 4. And then
Yeah, no. The nice thing about this, Gavin, is you just use what's given to you. Now, by the way, use substitution here, correct? I'm not going to take time to do this.
Yeah.
Let's set up another one. What if I said about then the x-axis? This is going to be 2 pi. Going from where to where, people? 0 to 2. Good. Let's just go ahead and fill this in. This is going to be 1 plus negative 2x the quantity squared dx. Now, what's my radius?
the whole
It is y, also known as 4 minus x squared. Now, the rule of having a single variable in your integral still stands, right? Can't have y at the x problem. You put in what it's equal to. Andrew, you hanging in? Perfect. Some of these guys tonight, everyone stick with me, no daydreaming. We're almost there, right? I'm going to allow you to use your graphing calculator on. So let me just remind you how to do this. Is everybody ready? What I'm going to do, since I'm using my graphing calculator, and so I don't forget it, I'm going to put this 2 pi back in. Everybody with me? So now what I'm going to do is I'm going to punch this entire thing into y1. I'm going to graph this because isn't this nothing more than the area under whatever this curve is from 0 to 2? By the way, if you got y's in there instead of x's, punch it into your calculator with x's. Who cares? It doesn't matter. The variables don't matter. Does everyone understand what I'm saying? All this goes into y1. You do second calc number 7, 0, enter, 2, enter. It'll shade it and give you the numeric value of the surface area. So it will be square units of area. That's it. Easy. Now, by the way, you know, it's not going to give you a picture of what this looks like, obviously, right? It's just going to give you the numeric equivalent for area underneath whatever this curve looks like. No one seems excited. That's cool. Come on. Woo!
Yeah.
It's pretty cool. Exactly. It's surface area. That's right, Gavin. All right. Real quick, I just want to work through one algebraic with you, and then I'm going to stop talking. Let's go back to arc length. What if I said, hey, let's do the arc length. Let's see, which one do I want to do? This one right here. So what if I had, find the arc length of f of x is equal to, let's do x to the 5th over 10 plus 1 over 6x cubed. Read it. And I'm going to go from 1 to 2. All right, here we go. Again, we're back to arc length, right? So you don't need any 2 pi r. All right, is this going to be the integral from 1 to 2 of the square root of 1 plus y prime squared dx? You'll notice I'm not writing it in there yet, right? Because this looks kind of like a horrible derivative and stuff like that, okay? All right. I warned you about some algebra, right? This is where the algebra comes in. So I just want to work through it with you so you guys can see it clearly, all right? So let's work on the innards here. And then hopefully it'll be integratable, okay? So first thing I'm going to do is derive this. Then I'm going to square it. Then I'm going to add 1 to it. Hang on, let me say this again. I'm going to derive it. I'm going to square it. I'm going to add 1 to it and put that expression into my integral. Excuse me, into my root. Okay, here we go. I'm going to write this as 1/10 x to the 5th. I'll write that as 1/6 x to the negative 3. This is y. Let's derive it. Here we go. Y prime. Caitlin, go.
It would be 10, so half x to the 6th. Or 4th, yeah.
Yep, wrong way. Keep going.
And then it would be negative 1/2 x to the 6th. Weird.
Wrong way.
Wrong way? Negative. Oh my god, negative 4.
I know it's really easy to go the wrong way, right? Look, we're integrating, but we got to derive first. So take 1 away from the power. There you go, people. We good? Sweet. All right, let's rewrite this. So I got y prime then is equal to, this is x to the 4th over 2 plus 1 over 2x to the 4th. Sorry, that's minus. Thank you. I think everything else looks okay, right? Sweet. Let's get a combinator. Come on, it'll be fun. This top and bottom by x to the 4th. This is the same as x to the 8th minus 1 all over 2x to the 4th. Nope,
X to the 6 maybe.
I think we're good. Same base at the exponents, right? Okay, good. I think I'm good here. X to the eighth minus 1 over 2x to the fourth, correct? All right, sweet. We're almost there. Now we got to square it. My advice to you is to keep it in a single fraction form. It's easier. All right, here we go. Isn't then y prime squared going to be equal to, what is that? X to the 16th minus 2x to the 8th plus 1. Well, that's a 2, not an 8. There we go. All over 4x to the 8th. Everybody with me? Got a foil at the top, don't you?
Yeah.
Yep. Okay. Square. Oh, sorry. Add 1. I already squared. Whoops. All right, here we go. I'm going to add then 4x to the 8th over 4x to the 8th because I have to have a combinator. Don't I? Bet your freaking baby I do.
So that's just-
So I got
just change
y
the same thing.
y prime squared plus 1 is going to be equal to x to the 16th plus 2x to the 8th plus 1 all over 4x to the 8th. That's correct, Gavin.
Yeah.
Wait a minute.
And then we square over the all.
Yeah, but wait. You can't because it's pluses and minuses. But I think I can factor the top. No, you don't seem excited. All right, here we go. Ready? This is going to be x to the 8th plus 1 quantity squared. All over 2x to the 4th, the quantity squared. Ain't it? Now, by the way, they have to write these so that they do work out. No offense, guys. You guys don't know enough integration to be able to get this done. They have to write these so that you can manipulate them. So these will end up working out to be factorable. Pilar, are you doing okay?
Yeah.
Please tell me if you're not.
So is the equation on the top right, is that actually the last equation?
Yeah, so that's after I added this, then I went up here, and then I came down here, and this is x to the 8th plus 1 times x to the 8th plus 1 all over 4x to the 8th, also known as 2x to the 4th squared.
So we're not including the plus minus? Like we're,
Yes, yes, yes. So y prime squared plus 1 is this. Because I had negative 2x to the 8th plus 4x to the 8th. Negative 2 plus 4 gives you plus 2, right?
wait, so then why does the y prime have a plus?
Equal.
Yes.
It's not equal.
The innards that I'm looking for is this. Good. I think it's the notation I'm using, right? It's just that this is the innards that I'm looking for. I'm developing the left-hand side and getting the algebraic equivalent on the right.
You just have the steps outside of.
Exactly. So guys, isn't this then the integral of x to the 8th plus 1?
You're missing the 2 to 1.
I am. Thank you. But hang on here. That's still a quotient. I don't think you works. No offense.
I'm offensive.
I understand why. What do you think we should do? Yes, Ben L. He's got it.
Multiply at the bottom.
Love it. All right, here we go. Ready? So isn't this going to be, we're going to take a 1/2 out to the front, right, Ben L?
Yep.
Bet your freaking bibby and bring this up to the top. That's going to give me x to the 4th plus x to the negative 4th dx. I skipped about 9 steps there. Are you guys okay with what I just did? I brought this up to the top, took the 1/2 out to the front. And distributed. Go. Taylor, what's this?
1/5 to the x to the fifth
Yep. Go. Taylor, go.
plus 1/4. Or is it negative 1?
I think so, yeah.
To the negative, or no, to the negative third. X to the negative third.
Mm-hmm. X to the -3 over -3. So I think that should be a 3 here, right? How we doing, people? We okay? I know. I am. Okay, now plug in 2, plug in 1, subtract. Yeah, people.
Yeah.
And you know what that gives you? Arc length of that curve. And it's about what we thought, right?
Yeah, exactly.
32 fifths minus 1/24 times a half minus a fifth minus. It's about right.
Oh, yeah.
Thanks, Kevin. Appreciate that. Thank you. Thank you. All right, thanks for hanging in. You see why I went straight to here and skipped the warm up. You should see Olivia's face right now. Okay, so here's what I'd like you to do. I'm going to give you everything. We got 1 hour. If there's something you would like me to do or talk about or explain, I'd be happy to, okay? Other than that, I'm going to come around, check some homework, let you guys get after it. You can work together. I need you working on calculus. Take a go get a drink, go to the bathroom. I'm good at that too. I just need to know where you're going before you go. All right? Perfect. Again, I want calculus being worked on, not something else. All right, put it on the board. Thank you. You may. Kevin, you're okay, right?
Yeah.
Okay.
I'm sad though, only you can laugh at my jokes.
No, I got you. I speak Gavin.
Yeah.
Yes.
Yeah.
I usually have another friend laughing off of this one, I have another retarded.
Like, I could,
And now I only have.
That's all right. I'm there for you, Gavin.
Yeah.
Yes.
pretty subtle. Yeah, like, that's, I'm just gonna.
Because like it's his favorite.
I was so tired.
Yeah, we have one every day. Until he the last week for like 3 weeks, it'll sit.
Right.
It's just.
It's just giving him emotionally fulfilling. It's not hard, it's just a thank you in advance for giving me.
All right, people.
Creating a positive relationship.
Does anyone have questions like on dishwasher shell? We doing okay? Yes, sir.
Well, I have a, like, when it.
Oh, wait. Hang on 1 second. Did we do 60 yesterday?
Yeah.
Yeah, just take out whatever I've already given you. Sorry. So, is that good?
Yeah.
Did we do 60 A and B and C?
Just did sales. So,
A, B, and D, maybe. Maybe I just can't read my writing.
We don't have to.
Setup only, by the way.
Which parts do you want us to like solve?
These.
Oh my god, we're gonna make negative.
By the way, hey guys, excuse me. Excuse me. I haven't looked at this lately, but I do believe some of these, they tell you that you can't integrate them. So make sure you read the directions and you can just set them up. But I think most of these you can get through by hand, okay? These obviously you're gonna use your graphing calculator on, okay? Okay, Sarah, go ahead, I'm ready.
Oh, okay, so, wait, let me,
Yeah, take your time. Helen, where are you going? Can you go to this room? Yes.
so I am slightly confused. Can you do 18 from homework?
I can. Give me the curves.
Okay, so it is, Michael's x squared and, Brian's 4 minus x squared.
Got it, so hang on here.
And then, rotating around the x-axis using shell method.
Got it.
I didn't understand.
I'm just a little confused, like finding the.
What number is this, Sarah?
18.
18. Guys, I'm gonna do number 18 if anyone wants to see. All right, and you said, Sarah, we're using shell, correct?
Yeah.
Got it. First of all, what do the rectangles look like?
There's this side.
Love it.
Horizontal.
Perfect. DX or DY problem? Going from where to where?
Going from 4 to 0.
I'm with you. What's the
Um,
radius?
Y. Right?
Keep it.
Use vessel length. Because how do you put the length in terms of Y?
Yeah, got it.
Well, you solve it for Y, like solve it for X. Solve each one for X and then. put them in there. Top one, solve.
Yeah, but hang on here. It's x1 minus x2, right?
Yeah.
This wasn't one of the problems in the homework, was it? Bet it wasn't. I bet you're going around the wrong axis. Yeah, you guys do see the issue with this, right? Mathematically, it's difficult because to get this length right here, isn't it x1 minus x2? So I can solve this in terms of y. Trouble with this in terms of y is difficult. So I wouldn't give you a problem like this,
It's
right?
around X equals 2.
It's x equals 2.
That's fine.
That's the problem.
Okay.
Look at this gap in front of me.
So by the way, Sarah,
Yeah.
on a problem like that, I would probably give you the option. So you could do shell. Like if you were going around here, I'd use washer.
Yeah.
I wouldn't force you to use shell because it'd be impossible.
And can you also do, one, like, 15 with like,
Yeah, we could do washer. Let me just do, while I got it on the board, okay? Around the x sec, right?
Yeah.
Okay. You agree dx, yes?
Yep.
You also agree, Zach, that it is washer.
It's from 0 to 3.
Yeah. Also, it's a dx problem, yes? Okay. Remember how washer works? You envision yourself standing on the axis of revolution, and you go to the far curve. What is that? That is y. These are dx problems.
So it's, 4x minus x squared.
Beauty. Minus the inner. Stand here, look to the closer side.
And so that's just x squared.
Yep.
Yes.
So, okay, I know on some of those problems, you have to like have a constant square and then you subtract the line. You know what I'm saying? So like, let's say you had, a cylinder from 0 to 2, and its radius is 300, right? And then you subtract the. It's the like one we used this morning where it's just a number, just 4.
Yes.
And then you subtract the function.
It was the graph, if I recall this morning, Zach, it was something like this.
And yeah, so you do the full length. But would you ever do this, like, start with a constant? and then
No.
subtract the-
No, because, here's why. There is no constant outer curve. Okay. Okay. You guys are right.
Yes, can I ask you a couple questions from the homework?
Yep, but give me 1 second because I was told Sarah I'll do hers first, then I'll get you guys, okay? Go ahead, Sarah, what do you got?
Okay, so, would you, process, we have like a circle, and it's semi-circle cross.
So it's a circular base, semicircle cross sections. Got it, okay. We'll say radius of 3. Semicircular cross sections, right? So. Tacos, well said. Volume of a taco,
1/2, fire squared height.
11.
my God.
Let's do some partial credit.
radius
still think that one's.
from,
And how do you know this one's DX? It doesn't matter.
There's not that many problems in the book, Zach. I'm just gonna give you perpendicular to the x-axis for all the different Nope,
it'd be,
it's 9 here, not over here. So what is this distance? By the way, Sarah, from there to there,
oh,
is from there to there. What is that?
oh,
Yes,
Yeah, I get that, that's not what I meant.
it's a dx problem.
oh, right, and then you.
Yes. And you go from -3 to 3 because that's everywhere.
Because these go, they're all semicircles, Zach.
The images I have are kind of cool.
They are cool, yeah, I know. I wish I could draw them better, but thanks, man, thanks. Are you good, Sarah?
Yeah, I have one more, but.
Okay, I'll bounce back and forth. Go ahead, Skylar.
Mine is number 15.
Yeah.
On page 457.
Okay.
And it's a volume one, and it's telling you to specifically use the shell method.
Yes, okay.
And then it's the lines y equals 1 over x.
Okay, hang on here. 1 over x, yeah,
Yeah. And then x equals 1,
okay.
and x equals 2, and y equals. And I just, I don't know, I just got stuck. Because I know that you do it in 2 parts and add
You
it.
have to. Are you having trouble seeing the 2 parts?
I'm having trouble, like, determining the length and the radius of the individual parts.
Easy. Okay, so we're going around the x-axis.
Yeah.
So it depends on where you draw these rectangles, right? So like if I'm just thinking about this in my brain, right? Here's one. But if I look a little bit farther down the road, you guys agree that as I go like around here, right? These will have constant length only up to that point right there. At which point they start getting shorter lengths all the way up. So I have 2 separate curves I have to deal with, right? So I have to think about these points of intersection. This is going to be 2, 1/2. And this is 1, 1. Because if I draw it up here, suddenly the length is defined by this curve rather than that curve. Which means 2 separate shell problems added together, right? 2 pi. It's telling you. Yeah. I agree. If I give you the choice, I'd never use shell. I'd use disk. Right? Wait, yeah. This is cruel and unusual to use shell, but that's okay. We got this, all right? So I'm going to first do these bottom parts, Skylar. 0 to 1/2, because these are dy problems, right? Then when I do the upper ones, I'm going to go from 1/2 to 1. You with me, right?
Yeah.
Love it. Okay, so all you got to do is get radius. Let's do the radius for each one. Isn't it true? The radius for this first one goes from here to here. What is that?
Y.
Perfect. By the way, Skylar, what's this radius?
Y.
Yeah. Nothing wrong with it being the same thing, because the thing that makes them different are these intervals. This y goes to 1/2 to 1. This y goes from 0 to 1/2.
Okay.
Yeah, I think I'll get to it.
Okay. Now all I gotta do is get the length, right? So take these one at a time. What's this length right here? Good. Yeah, that's all. By the way, to get that, didn't you subtract the 2 x's? X1 minus x2 is 2, take 1 minus 1. Right on. So what's this?
One over x.
You're saying this is y. Let me back up. Skylar, do you need subtraction for this?
Yes.
You know you need subtraction. The minute you realize you need subtraction, if you're measuring this direction, right curve minus left curve. If you're measuring this with subtraction, upper curve minus lower curve. This has got to be rightmost minus leftmost. So isn't this x1 minus x2? x1 minus x2 gives me this. I'm just going to pencil this in for a second. I can't have x's. These are y values. So what's x1? No. That's x2. It's rightmost minus leftmost. What's this? It's going to this curve, Olivia.
Y,
Closer. This is x, also known as 1 over y. What's this?
one.
That's 1. Skylar, did you see what I'm doing there?
Yeah.
Okay. You really got to focus on rightmost minus leftmost. Make sure you're using the curve that you're going to. That's why this is not 1. It's this curve right here. And you have to keep in mind that that's x. So you got to rewrite it.
I'm gonna check right now, but I feel like the solution's are better than this.
Check right now.
I'm checking.
Your eyes glazing over, Caitlin. A little bit. It's a lot. I know. I get it. It's a lot. I get it.
So wait, on this, the minus 1, I get the x, but that's just from the y-axis to the left.
Yeah.
And then the minus 1 is.
Oh, I'm done.
Okay, so we're finding it from 1 to 2. Or 1, yeah.
x1 minus x2.
Like, I'm there algebraically, it's just
See,
like, hard to visualize.
It is.
They just distributed the Y.
Gotcha.
That's, yeah.
So they got, oh, that's where they got the 1.
Yeah, I was like.
Perfect. Pilar, do you need me? Are you sure?
Yeah.
Don't hold back.
Is it? I have to drop.
Yep. Of course. No, no, you, listen. You mean, like this thing? Or you're just throwing in the, like you draw, for disc, shell, and washer, is that what you're saying?
Yeah.
You have to draw this?
Yeah, I'm really.
For sure.
Okay.
No, I do too. That's the reason I always draw it, because it's like virtually impossible if you don't
I like
look, right?
draw with paper, but too steep, because there's like messy
Yeah.
picture, and then I like think that-
Use a lot of paper, Olivia.
Yeah.
I'll give you as much paper as you want. Just make it really wide, really tall.
What I have to do also is I shade in the area I'm trying to find lightly.
Yep.
That's just helps.
Love it. Good.
It's like, yeah, sometimes I don't know what you're saying.
It doesn't matter, you don't have to.
Love it. Anything else? Is it getting a little better? Okay.
I just still get like thrown off.
It's super, super easy. It's one thing that will help you though, just keep in mind what I said. If you're ever going this way and not coming from the x-axis, it's always upper minus lower, always. Y1 minus Y2. If you're going this way, not from an axis, it's always rightmost minus left. It's always. I think that's what's sticking in your head, which is understandable.